So good evening all. We can wait for 5 minute maybe. After that we can start. Maybe around 6 5 we can start the class. We can wait for 5 minutes. Okay, I think we can start the class. Let me share my slide. Just a minute. Share the screen. Okay. Yeah. So I think my screen is visible to all. I think we can start the class. Okay. Okay, so good evening all. Welcome to this course. The course is Electrochemical Technology in Pollution Control. So I am Suvankar Mandal from Indian Institute of Science. I am a TA of this course. So whatever now we are in sixth week. So here we'll discuss the electrochemical sensor. So before this class, we have discussed so many things about Karl-Fischer titration and what are the Karl-Fischer reagent and how it is to work and how the color is changing and why the current response is to come in Karl-Fischer reagent, and from there we get to know how much amount of water is there in your solution, So that thing we have discussed, and different type of problems on this Karl's Fisher titration. We have discussed some numerical problem also we have discussed, and along with that we also discussed different polarographic problems, different why we need to use mercury drop electrode, why mercury is useful as a electrode in polarography. So all these things we have discussed in last class. So this week what we will discuss, that electrochemical sensor. So I am not going to discuss so much details of electrochemical sensor, because as professor already discussed this thing. So I think, okay, just a minute. Let me check. My microphone is, yeah, my microphone is on. So, hmm. So, okay, this in this class, what we will discuss cyclic voltammetry. So, before going to this, I want to mention that why we need discuss all these things, because when I was going follow the class this week, there is we are discussing different type of electrode, three electrode setup, but I feel that we need to know something, that why we need three electrode setup. And in recent time, people are more interested on cyclic voltammetry rather than polarography or control growth mercury electrode, because mercury is poisonous. So people used to avoid nowadays to use mercury electrode as a working electrode. So for this, we need to discuss a little bit on cyclic voltammetry. So I will not go discuss so much on cyclic voltammetry, because these things is kind of extra. So I will just go through this cyclic voltammetry, why we need three electrode setup, and why supporting electrolyte is required, what is supporting electrolyte, and what is voltammetry. So all these things we'll discuss today. And after that we'll discuss why suddenly three electrode is required, because when we used to discuss galvanic cell or electrolytic cell, they are use two electrode, one is cathode, another one is anode. But when we are talking about polarography, that time we are using three electrode, one is counter electrode, one is working electrode, other one is reference electrode. So why we need three electrode setup, so that things we'll discuss today. And cyclic voltammetry also we'll discuss. Other things is potential, yeah, and potentiometric titration video. So basically we already discussed potentiometric and conductometric titration in theoretical. So once I think before 1 year I was the TA in ISC, some UG practical course. So there we have done some conductor voltammetric and conductometric titration. So that practical video we have, because that time corona is going on, so we recorded that video. So we are fortunate that that video we have. So that video I will show you how the instrument or how the titration we used to do. I think most of the people know, but whoever in BSc or class 2 level, so they I think that will be helpful for those student. Okay, and after that we will discuss the previous year assignment question. So I think after this we can discuss some of the previous year question. After that we will see the video, this potentiometric titration video. After that some problems on electrochemistry which is came in CSIR UGC net. I think some of the student they are in MSc or BSc, so this problem solution session will be helpful for that student. Means maybe BSc, if they are interested on JAM exam, then that will be helpful, because in JAM exam also in the syllabus electrochemistry also there. And in MSc also whoever studying, so in UGC net there electrochemical electrochemistry part also there, so that will be helpful for them. Okay, so we'll discuss this thing today agenda all 5 point. So let's start with voltammetry. So what is voltammetry? Voltammetry refers to a group of electroanalytical methods from which you acquired information about the analyte by measuring current in an electrochemical cell as a function of applied potential. That means you are applying the potential in the cell, electrochemical cell, and you are measuring the current, and from that voltage current voltammogram, that is called the voltammogram. So from there you can get the information about the analyte. So that is in general it is called voltammetry. So it is developed by, from the polarography, which already we have discussed how it is to work and all these things. A particular type of voltammetry invented by the this chemist and Jaroslav Harovsky in early 1920s. So this variable excitation signal in voltammetry. So what is excitation signal in voltammetry? Basically, you are excite the analyte with different variable potential and on the working electrode. So you have different type of electrode like working electrode, reference electrode, and counter electrode. So you are exciting the, or you are applying the potential on the working electrode. Okay, and this excitation of the voltage, or when you are applying the voltage, that will excite your analyte and it will give the current, and that current response will measure as a function of voltage or as a function of time. Okay, so there is different type of voltammogram is there, like linear sweep voltammetry. So LSB used to tell. So I can write here linear sweep voltammetry. Okay, why it is called linear sweep voltammetry? Because you are applying the potential with respect to unit time, maybe in second, or with respect to time, and with time you are increasing the potential linearly. So you can see there is a potential versus time. If you plot, it is what is called constantly increasing, so it is linearly increasing. So for this it is called linear sweep voltammetry. Okay, now there is another also there, differential pulse voltammetry. So differential pulse voltammetry, what is there? So here you are applying the potential, suppose millivolt per second. Okay, so this is we also call scan rate. So the scan rate unit is millivolt per second. So here basically you are applying the potential per unit second or per unit minute. It is usually people used to apply per unit second. And differential pulse voltammetry, what is that? So it is linearly increasing. After that you are applying the potential for a some times. So when you are applying, suppose you are applying 5 millivolt for 10 minutes. Okay, so that means that this is called pulse. Okay, so you are applying the current, what is called potential, and after particular time you are increase the potential, and for constant potential you are applying for 10 minutes. So it is like this. When you are applying the potential, after that you are giving the relaxation. When you are giving the relaxation, the potential is coming down, because system want to go the equilibrium. So you are disturbing the system up to here. After that it is coming down to the equilibrium or stabilized form. Again you are applying the constant potential like 5 millivolt for 10 minutes, so it will come to like this. So this is called the differential pulse voltammetry. So there is another type of voltammetry also there. So like square wave voltammetry, where you are what is called you are applying the constant potential, and whatever time you are applying the potential, that much time you are keeping for relaxation. So that is called square wave potential. square wave voltammetry. Okay, another is triangular. So this is basically cyclic voltammetry. What is cyclic voltammetry? So you are linearly increase the potential. So you can see this and these are same. So if I draw this part, so this part and this part is the same. So this is one part, and again you are applying the potential constantly, or and after added some point, suppose this is a1 and this is a2. So you are started from a1 and it is going to a2, again you are coming back to the a2 point. So this is kind of the triangular kind of thing. So in this case you used to call cyclic voltammetry, where you have fixed the potential window. Suppose you have fixed the potential from 1 volt to minus 1 volt, and once you are started negative polarization or negative potential shift, so you are started from the 0. I can write this is 0, this is plus 1, this is minus 1. You have started from 0 to minus 1. After that again you are coming back to the plus 1, again you are coming back to minus 1. So like this. So when you are doing like this, if you plot the potential as a function of time, you will get this kind of graph. Okay, so this is called different type of voltammogram or polarography you will get. So different type of voltammogram like linear sweep voltammetry, then differential pulse polarography, and then square wave voltammetry, then cyclic voltammetry. Now question, this oxidation reduction we are talking so much, and we already have discussed so many things on oxidation reaction, reduction reaction, acid base reaction. So how these things used to happen? So you can see, this is one cartoon. So suppose the reaction is happening in the solution. This is called homogeneous electron transfer. What is homogeneous electron transfer? Suppose you have two component, that is A and this is B. Okay, and these A and B both are in the same phase. If they are in the solution state, both are in the solution state, and they are transferring the electrons. So that is called homogeneous electron transfer. So let's you can see this is a ferrocene and you have the cobalt complex, and you can see the what is called the energy of orbital of ferrocene is lower than the energy of orbital cobalt complex is high. So what will happen, that this electron, when the oxidation this energy is high, so it wants to go to the lower energy or stabilization, so it will transfer the electron to the ferrocene. So then ferrocene initially it was in positive, so as one electron is accepted, so it will go to ferrocene neutral and it will become a positive. So that means from the cobalt complex to the electron transfer is happening to the ferrocene positive ion. So these two products are in the same phase. For this it is called homogeneous electron transfer. Okay, then next is the heterogeneous electron transfer. So what is heterogeneous electron transfer? Whatever we are doing the electrochemical studies, so you have the electrode which is a solid, and your analyte you are dissolving the electrolyte, that is a solution. That means when the electron transfer is happening from the electrode to your electrolyte solution, that case one electrode that is in solid state and your analyte that is in the solution state. So these two are in different phase. For this it is called heterogeneous electron transfer, because from your electrode to your ferrocene, that is the analyte, the electron transfer is happening, and that's why it is called heterogeneous electron transfer. So when in electrode you are connected with the potentiostat, so when it is connected to potentiostat, that means you can apply the electron or you can abstract or subtract the electron from the analyte. So if you negative sweep if you do, then what is called your electrode Fermi level, that will increase the energy. So when it is increased and it is merged to the homo or LUMO energy of the ferrocene, it can donate the electron to the ferrocene, so it will go to the ferrocene neutral. So this is called the what is called ferrocene, this is called the heterogeneous electron transfer. So now when we are talking cyclic voltammetry, so how it looks like? So it used to looks like this. So you have a current as a function of potential. So okay, there you will get this kind of peak. Okay, so this peak representing some Faradic reaction where your electron transfer is happening. Okay, so in polarography, what we observe, that this kind of things is to observe. So some steady state is to observe. So these things is representing. So this thing is representing some redox process or Faradic reaction. Faradic reaction. So here also these things are representing some Faradic reaction. Okay, so the dark kind of shape is coming. So we will discuss more about this, why this dark shape is coming, all these things. So slowly you can proceed. Okay, so this presentation or cyclic voltammetry is to present in two convention. One is US convention, other one is IUPAC convention. Okay, so IUPAC convention, and what is the difference of IUPAC and US convention? So both case it is representing same thing only, but the convention is that you can see the potential or x-axis. In the US convention, your lower potential is on the right side and the high potential on the left side. On the other hand, IUPAC convention, your high potential is the right side and low potential on the left side. So people usually nowadays prefer to present your data in IUPAC convention. So when in the US convention, the lower part, the lower dark shape deep, that is represent the oxidation, and the higher deep, that is reduction. Okay, and on the IUPAC convention, the opposite. So lower part representing the reduction and upper part representing the oxidation. Okay, so this is the thing. And now it what is this high and lower potential? Basically, suppose you have a electrode and you are 0, this is +1 and this is -1. So this is positive value, this is the high potential, and this is low potential. Okay, got it. So this is the simple thing. Now this current, so we are getting the current. So this is different type of current we used to get. So three type of basically current is there. One is diffusion current, two migration current, three convection current. Okay, so these three current is there, and Nernst equation I think we already discussed. E cell is equal to E naught cell RT by NF ln ox by rate. So this already we know. So I am not going to discuss that thing. So cyclic voltammetry, how it looks like, so you can see these things. So this is cyclic voltammetry plot. Okay. So now this is the electrochemical cell. Okay. So this is the electrochemical cell. So nowadays in all research group, people used to do 3 electrode setup where people used to use this kind of thing. So polarography, also we have a container and we have a working electrode, reference electrode, and what is called counter electrode. So here also electrochemical, this is the electrochemical cell when you will do the CV, all these things. So similar kind of electrochemical cell is there. So there, here you can see 3 electrode is there. So this is this black one, this is the working electrode, I think. Yeah, so this is the it is written, this is the working electrode, and this is the reference electrode, and this one is counter electrode. Okay, so now usually why we need this 3 electrode setup, or why we need the solvent. So how we can choose the solvent? So different type of water, usually in aqueous solvent we use water as a solvent. So why we need to use water as a solvent? Or I can change the question in this way, that how you can choose the solvent. Okay, so what are the properties is required, or characteristic is required to use as a solvent in electrochemical cell? So these are the properties. So it is a liquid at experimental temperature. So whatever temperature we are using, in that temperature it will be liquid, and it dissolve the analyte and high concentration of the supporting electrolyte completely. Okay, so when you are dissolving the supporting, should be completely dissolved. It should not be a disperse or kind of thing, or colloidal kind of thing. So in that case, the result whatever you will get, that may not be the appropriate. Okay, and it is stable towards the oxidation and reduction in the potential range of the experiment. So whatever potential range you will choose, in that potential range, the solvent whatever you are using, that should be stable, means solvent dissociation should not be happen. Okay, and it does not lead to deleterious reaction with the analyte supporting electrolyte. Okay, that means suppose some reaction is to happen, suppose you have used some analyte and you dissolve in the solution. When you dissolve in the solution, it can react with the solvent. Okay, and some other product can form. So but when you are choosing the solvent, it should be stable to your analyte, or as well as in the supporting electrolyte. Okay, and it the final one is, and most important, it should be purified. Okay, supporting electrolyte, a supporting electrolyte will be this kind of property should be there. It is highly soluble, which we already have discussed, and it is chemically and electrochemically inert in the condition of the experiment, and it can be purified. Okay, so these 3 properties should be there, and this most important is the electrochemically inert. So what is the meaning of the of electrochemically inert? So basically, suppose you are what is called your potential and voltage, this is +1 and this is -1, and you are doing some cyclic voltammetry, and you will get this kind of graph. Okay, so this is for your analyte, and what is called in this potential range. So whatever -1 to -1 to +1, in this potential range, your supporting electrolyte should not show any redox features. Okay, if you do only for supporting electrolyte, then you will get this kind of straight line. Okay, that means in this range no redox process is happening, your supporting electrolyte is stable. So this is the thing. Okay, so now I think this is not required for this. So whatever I have discussed earlier also, so you are starting the potential from here. So this is the A, and you are started the sweeping to D, and you are reaching here D. This is the potential, time versus potential. So D, after that you are coming back to the G point. So this is coming back to G point. In this case, G and A point are in the same potential range. Okay, so this is the thing. So now this is the plot of time versus potential. Now if you plot current versus potential, you will observe this kind of graph. Okay, Now some of the question will come in mind that why this reaction is happening. So this is what is the driving force of this reaction. So basically you are attach your electrochemical cell, what I have shown in the previous slide. So that is attached with the potentiostat. So in the potentiostat you can apply the potential. So this applied potential is the driving force for the reaction. So basically this potential, this dark shape as I have mentioned, this is representing some redox reaction or Faradic process. Okay. Now second question, why are there peaks in cyclic voltammetry? This question already have answer, because these things are representing basically some redox process or Faradic reaction. So now why dark shape of the cyclic voltammogram? So the question is why this kind of dark shape is there. It can be like this, or what is called like this kind of thing is should it can come. Why this kind of thing is coming? So there, for this answer we already discussed about the diffusion process. So diffusion coefficient we already discussed in polarography. So basically you have the electrode, this is the electrode, okay, and your analyte, I can change color. So you have the analyte. Okay, so in the analyte, suppose you have taken Fe3 plus solution. Okay, now when you apply the negative potential, then what will happen? All the Fe3 plus is to come here. So Fe3 plus is going to Fe2 plus. Okay, then when you are applying the potential and Fe2 plus is going to Fe3 plus, and it is going diffuse to your bulk solution. As a result, there should be a concentration gradient will concentration gradient concentration gradient will form, because in the electrode surface you have Fe2 plus, and on the bulk solution Fe3 plus is there. So as a result, Fe2 plus with time, if you see that Fe3 plus coming to your electrode surface will be difficult. So for this, when the reduction process or it is reach a particular potential where your Fe3 plus can reduce to Fe2 plus, so that case what will happen, you will get see this kind of hump. Okay, after that when some of the Fe2 plus is going to Fe3 plus is going to Fe2 plus, there will be a concentration gradient. That means initially whatever way Fe3 plus is coming, with time lag it will decrease. So the rate of Fe3 plus reach to electrode will be decrease. For this, it is decreasing the current value and it will come to the end point. And when Fe2 plus is going to Fe3 plus, you will see this kind of thing. Okay, so this maximum, why after maximum depletion is happening? Because initially whatever way only the Fe3 plus is there, and after that when Fe2 plus is coming, so there is a diffusion gradient or concentration gradient is there. So the rate of reaching to the electrode surface with time, it is decreasing. So for this there is a depletion. Okay, why the reverse peak is shifted? So the question is there, this is the maximum, this is the maximum. So why it is not opposite, exactly opposite to each other? So basically this is already I have mentioned. So this is the diffusion coefficient or concentration gradient. Okay, so where should we start the scan? This is very important question, that when you are doing the experiment, so where we should start. So basically when we are putting 3 electrode in your electrolyte solution, so that is called the equilibrium potential. So you should start from the equilibrium state. Okay, that means that is when it is in equilibrium, or you are dip your electrode in the electrolyte solution without apply any potential. Whatever potential is giving, that is called OCV. So open circuit potential. Okay, that is the thing. So when you are not applying any potential in the electrode, you just dip the electrode in your electrolyte. So that time whatever potential will show the system, the difference between the reference and working electrode. So that is called open circuit potential. Okay. So now more important question, why we need 3 electrode? Okay, this is the question that why you need 3 electrode. Okay, because when we are discussed earlier also, so you have the zinc plate, here you have the copper plate, and this is zinc, and in electrolyte you have taken zinc sulfate, and electrolyte you have taken here copper sulfate, and this is connected with salt bridge. So there is we are measuring the potential with two electrode setup. But why you need the 3 electrode setup? Okay, this is the question. So why you need 3 electrode setup? Because what the function of electrode we already discussed, that in working electrode we are measuring what? Applying potential, measuring current, and applying potential with respect to reference electrode. Okay, so we are measuring the current on the working electrode, and you are applying the potential with respect to reference electrode. See, this current also we are measuring with respect to reference electrode. So when you are measuring current or response current, that means there is some redox process is happening. So if you have 2 electrode, so if you have 2 electrode, one is cathode, one is anode. So this cathode is the working electrode, I can say, and anode is the reference electrode. Okay, so if cathode reduction is happening, then anode oxidation will happen. So if the reduction is happening, that means some electron process is going on. So electron is transferring through this electrode. So and in the reference electrode also oxidation is happening, means electron transfer is happening. So if the electron transfer is happening, so whatever potential you are getting with respect to reference electrode, the working electrode potential with respect to reference electrode, that is not the exact potential. So then what we can do, that we can introduce third electrode. We can introduce third electrode. What is the function of third electrode? That is called counter electrode. What is the function of counter electrode? Basically, you can, here you are what is called electron transfer is happening, and that electron transfer, suppose cathode reduction is happening. Reduction is happening means it can accept the electron. So if this reduction is happening here, and the counter electrode, if oxidation can happen, which is initially happening on the reference electrode, then what will happen, that on the reference electrode there is no reaction is happening. So whatever potential we will get from the reference electrode, that will be constant. Okay, so that means on the working and counter electrode you are measuring, I can write here, working and counter electrode you are measuring current. And working and reference electrode, you are measuring or applying potential. So that in this case, what is the facility that you are getting whatever potential, that is the accurate potential, because when you are taking some reference, that reference should be constant with time, or whatever working condition or whatever reaction condition, in that reaction condition it should be constant. Okay, so whatever, there should not be any changes is there. So this current value whatever, so that we can measure in the case of cyclic voltammetry, so that is called Rayleigh-Sevig equation. This Rayleigh-Sevig equation, ip, peak current, this is basically here, this is the called peak current. Okay, so this peak current, that peak current is equal to 0.446 NFSC naught NF nu D2 by RT. So what are these terms? So this N is the number of electron, F is the Faraday constant, A is the area of working electrode. Okay, and C is the concentration of the analyte. And R and T, all this thing you know, A and F, this nu, this is the scan rate. What is scan rate? Scan rate, basically you are sweeping the potential at a constant time. Suppose I am a scan rate, suppose 10 millivolt per second. Okay, so scan rate is volt per second, this is a unit. So 10 millivolt per second. What is the meaning of this scan rate? So 10 millivolt per second means each second we are applying 10 millivolt on the working electrode. Okay, and D naught, this is the diffusion coefficient. Okay, so this is the thing. Now when you are doing these things, so there is some of the term is there. So that is one is called reversible process, another one is called irreversible process. So what is reversible process? In reaction or in chemistry, we know that suppose some reaction is happening, A plus B, it is going to C plus D, and in the reverse process C plus D, again it is coming to A plus B, then that is called reversible process, and the forward and backward rate of the reaction is same. Okay, so in reaction we used to tell like this, but if the what is called A plus B is going to C plus D and the reverse process is not happening, then that is called irreversible process. Okay, so that is the thing. But in electrochemistry, what is reversible and what is irreversible? So basically if you see here, so this is the forward reaction and this is for backward reaction, so both process is happening in the electrochemical shape. So now we can tell that it is reversible if the peak current, this is the this dot line, so this is the peak current for this one. So no, this is the peak current for this one and this is the peak current for this one. So if the peak current for forward and for backward reaction is same, then we can tell that this is a reversible process. Another way to check this reversible process, the peak separation. So this is the cathodic peak and this is the anodic peak. So sorry, this is the anodic peak and this is the cathodic peak. So these two peak separation, if it is 0.0592 by n, then we can tell that is the reversible process. So on is irreversible process. So slow electron transfer kinetics result in del AP exceeding the expected value. That means if the peak separation for anodic and the cathodic is not same, it's not this value or it is bigger than this value, then we can tell this is the irreversible process. So there is another term also there, that is called quasi reversible. So what is quasi reversible? So quasi reversible basically it is in between the what is called reversible and irreversible process. So in irreversible process we will get only one peak. So if it is like this, so it will be like this. So you are getting one redox peak. That means only one reaction is happening. That means forward reaction is happening, backward reaction is not happening. Okay, and quasi reversible means you will get the peak, or what is called backward peak you will get, but the peak current value for cathodic and for forward and backward reaction will not be same, and it will be separated so much from the one peak to another peak. Okay, so this is the thing. Okay, I think this that's all about the cyclic voltammetry. So we can discuss some of previous year assignment question. After that, we will see potentiometric titration video. Okay, so this is the first question. The processes of plating one metal onto another by hydrolysis known as hydroplating, carbon plating, electroplating, none of above. So what will be the answer?
Electroplating.
You can tell what will be the answer. So the cyclic voltammetry part, is it clear? If anything is not clear, you can ask the question also now also, or you can ask on the end also. Okay, so the cyclic voltammetry, that is quite means now in we used to do the research. So during that time all people used to do the cyclic voltammetry, which is the primary tools to know if some redox peak is there or if some redox active pieces is there. Then we can get to know first things we used to do this cyclic voltammetry. Okay, so I think Barun has written this electroplating. Yeah, that is the correct, because basically you are plating the one metal. Suppose I can take some example. Suppose you have taken copper sulfate solution, where copper sulfate, copper 2 plus, and SO4 2 minus is there. So you are deep, suppose some other material, suppose zinc, I can tell zinc. So zinc plate you have taken and you apply the potential where copper is going to copper not. Okay, so that then it will plate on the electrode zinc surface. So that's why it is called electro plating. So hydrolysis, hydroplating, it is not hydroplating. Hydroplating basically there is no such term is there. So as you are taking the water or something which is acting as a electrolyte or solvent. Okay, so the question is electroplating is the right answer. Okay. So the next question is ion exchange electrode can be prepared by using an organic liquid ion exchange with, there is four option: hydrophilic membrane, hydrophobic membrane, am, amphiphilic membrane, and any membrane. What will be the answer? Ion exchange electrode. By the way, what is ion exchange electrode? We already discussed. Yeah, Barun has written hydrophobic membrane. Yeah, it's true, because what is called when you are taking the organic liquid, so basically it should be hydrophobic, so that when you are dipping the electrode with the some aqueous or hydrophilic electrode, it should not mix with the your electrode solution. Okay, so only the ion from the electrolyte to your ion exchange electrode, so only the ion can exchange through that. Okay, so that suppose you are exchanging the proton plus in the case of pH meter, so proton used to exchange, so from there you used to get the pH of the solution. Okay, so the next question is iodide selective ion ICE can be represented as, there is four equation is there: AgI, hydrogen iodide, membrane, then KCl. This representing the salt bridge, as we already know. Then Hg2, this is mercurius or mercury electrode, and this is AgI HI. So what will be the answer? A, B, C, D. Take little water. Yeah, Barun has written A. Yeah, A will be the answer. So basically means what is called your ion exchange iodide selective ISA. That means your iodine will be there, and in the iodine in your one electrode site AgAgI you have taken, and in with that you have taken the HI. So your ion, common ion, is the iodine minus. So which this is in one container, and which will be separated by a membrane, and another component your reference electrode is there. So this is the thing. So I think this is the thing. I think we can see the video for the potentiometric titration, then that will be more understandable, because we are what is called discussing the theoretical class, but I think it will be more understandable if we see the experimental setup, how people used to do this experiment. Okay, so I think I can show the video. I think this one. Okay, files, class material, and this video also I can share with you people. Okay, so you people can see this thing, uh, and I think we can increase the speed so that we can quickly discuss the thing, because this is 30-minute video. I think no need to see quickly. I can tell what we are doing. So this is the potentiometric determination by mixing of halide. So basically 3 halide we have given, some chloride, bromide and iodide solution, and from there how much concentration of iodide, to how much concentration of bromide, how much concentration of chloride iodide was there. So that things we have calculated from the potentiometric titration. So this is in we used to do in UG course in ISC. So that time Dr. Vivek Tiwari from the SSU department was the course instructor, and Cynthia Jana, he was the lab instructor, and I was the teaching assistant of that course. Okay, so this is the things, and okay, I don't know why it is not. Okay, I don't know why it is not playing. Strange. It should play. Is this recording for this? It is not playing or what? Okay. Okay, I think there is some issue. This video is not playing. Okay, no issue. I can share this video. I can download and I can share this video with the in the Google Drive. I can put in that folder so you people can see the this video so that you will get more idea how people used to do potentiometric titration, all these things. So I can see that this what are the chemicals is required. That distilled water you have to you require, and silver nitrate, which is a silver nitrate, because if you use silver nitrate with different type of halide salt, so silver chloride or all these thing will be form, which will precipitate will form. So that things there. And potassium chromate, that is the indicator, and pasco ORP probe, this is the potentiometric electrode. So basically whatever electrode, I think professor also discuss in the class that we need, there is a means 10,000 or 15,000 electrode is available, which is means user friendly and you can carry. So that things is there. So that is one electrode is pasco ORP probe electrode. So and burette volumetric flask, all these thing is required. So basically this is I think this all the measurement how we people means student can do. I think this is the thing. I will go directly to the pasco meter. So I think this is the titration where we are just standardizing the silver nitrate solution with standard what is called silver sodium chloride, because sodium chloride is the primary standardized and silver nitrate is to standardize with the primary standard. Then I think where is that one? I don't know why. Yeah, this is the Pasco electrode. So I think yeah. So this is this kind of thing. I think. So means this is what is called Bluetooth connected. So you can connect with your device. Means your laptop, and there is a software where these things is there. So means this device can connect it with your software in your laptop, and you can do the conductometric titration, pH meter titration, as well as potentiometric titration. So this electrode is quite flexible, so it is basically connecting with the Bluetooth, and you can give how much volume of silver nitrate you are adding. So I think in this whatever it is dipped in the beaker, so in that beaker you have the glassy carbon glass electrode, whatever we have discussed in the class. And in the glass electrode you have ion exchange membrane is there, so that things also there. You have reference electrode also. So I think I don't know, it will be very good if we can plot what is called play the video, but no issue. You can see. Okay. Yeah, so there is a some jump or something we told, no. So here you can see in the graph also it is showing some jump. So this is representing one equivalent point, and other equivalent point also. So these three halide is there, for these three jump is there. Okay, so I think yeah. So now you can see there is three jump is there. First initial jump, then second initial jump, then third jump is there. So these things is there. I think I will share this video to all you people. So I think it will be very helpful to you. From there you can get the equivalent point and how much compound or how much analyte is required to neutralize the NaCl or sodium Cl solution with a silver nitrate. So you will get the information that in the unknown sample how much halide concentration is there. So I think these things I will share, I will download, and in the Google Drive I will put. So that will be, I think, good. Okay, I think I don't know why this video is not playing. Okay, now we can come to the presentation. Okay, so this is next question. So in grand plots, antilog of NF by 2.303 RT versus reagent volume is used to determine nature of the test solution. Option B, the slope of the test solution. Option C, the concentration of the test solution. Option D, the pH of the test solution. So which one will be the answer? Okay, Varun, concentration of the test solution. Yeah, that is the correct, because this is the Grant's plot of weak acid titration, where you can see this is the acidic Grant function and there is the intercept. So if you plot the intercept which is touching with the x-axis, so in the titrant based volume, so in the x-axis you have the volume. So from here you will get the intercept. So from intercept you will get the concentration of the analyte. So this is the C is the right answer. So which among the following is not a part of an electrochemical sensor component? So gas impermeable membrane, option B reference electrode, option C electrolyte, option D filter. Barun has written B. Is the Barun for B? You are telling B for question number 5. You are telling B. I did not get because I just missed. It is earlier question option, or yeah, I think this is for question 5. You are telling option B reference electrode. Okay. So I can okay, whatever we have discussed in the okay, B for 5. Okay, so you can see the picture for what is called electrochemical sensor. So this is the part where you can see this is the counter electrode you have, which is sensing, and it is deep in the electrolyte. So this blue color reference, and you have the reference electrode, and on the top of that sensing electrode is there, which will sense particular what is called components of gas or CO2, anything is there, so it will sense. Okay, and on the top of that red things, which is hydrophobic membrane, which we will already discussed that for hydrophobic membrane we used to use. Okay, then capillary diffusion barrier is there here. So that means you have a gas impermeable membrane. So this hydrophobic membrane and this capillary diffusion barrier, which is the gas impermeable membrane, so that is correct. Then reference electrode, we have reference electrode, so that means in the sensor reference electrode is there. Then electrolyte, so you have the electrolyte, so electrolyte also there, but you don't have any filter. So means which can filter your gas or something. So that means which among the following is not a part of electrolyte? Filter will be the answer. So answer option D will be the answer. Okay, so question 6, an electrochemical cell is also known as amperiometric gas sensor or microfuel cell because it generates fuels it generates current, it generates water or carbon dioxide? None of these. What will be the answer? Can anyone tell? An electrochemical cell is known for amperometric. What is amperometric? Ampere, from ampere to amperometric is came. Ampere means current. Okay, so current, sorry. So current means current is to produce. So here you can see it generates water or carbon dioxide. No, it is not producing any water. It generates currents because in what is called electrochemical cell, what is to happen? You have the electrolyte, you have the electrode, and some redox process is happening. So when the redox process will happen, process will happen that will give you current. Then what is happening? Chemical energy converting to electrical energy. Okay, so that means B is the answer. Next, zinc, cobalt, chromium, iron, nickel, etc. fall under the categories heavy metals, soft metals, coins metals, electroplating metals. I think these things professor have discussed in the class. Yeah, it is heavy metal. So I think it is quite easy question because we already know in the from the class that what are the heavy metal, what are the soft metals, all these things. Okay, so next question. AgAgCl electrodes are dash electrodes, non-polarizable electrodes, polarizable electrodes, neutral, none of above. What will be the answer? AgAgCl, this is, I can give a hint, that reference electrode. Now you people can tell. What will be the answer? AgAgCl. So basically, what is to do, reference electrode AgAgCl, it is quite famous because for non-aqueous solvent most of the people use AgAgCl. So some Ag wire is there, and on the Ag wire some coating of AgCl is there, and which is deep in capillary reference some solution, that is 1 molar KCl solution. Okay, so that means with respect to reference electrode we are measuring the potential, so it should be non-polarizable, so that with time or with period of reaction there is no change in the potential. So the option A will be the answer. Okay, so next question. Ion selective electrodes are useful because they have lower linear range and higher detection limit than the pH electrode. This statement is true or false? So ion selective electrode is useful. Why? It is more detection limit is higher than the pH electrode. That is true or false? Anyone can tell? It is true, no? Ion selective electrode we have discussed in the means we have seen in the class that ion selective electrode, it is useful because it is what is called lower in range and higher detection limit. A copper coating is given to aluminum or magnesium metals to prevent the attack of acid on aluminum and magnesium, provide a base for further plating, prevent attack on aluminum through pores in zincification, to provide each of plating. What will be the answer? Answer, boron has yeah, it is correct. Prevent attack on aluminum through pores in zincification. Okay, so next question. Okay, we'll discuss some of the UGC net question. Okay, so I think it will be quite good. We can discuss some questions so that whatever previous year question or which type of question it is to come in the exam. So although we are discussing or we are reading this course as a pollution control basis, but I think it will be good that whatever we are reading or whatever we are learning, so from there how we can solve the question in what is called UGC net. If some people who are doing MSc, so if they want to give the UGC net or GATE exam, I think that case it will be very helpful. Okay, so it is came in CSIR net June 2016. So the question is, in the iodometric titration of solution sodium thiosulfate, which is Na2S2O3, with acidic dichromate solution. So 25 ml of 0.1 molar dichromate requires 25 of X molar thiosulfate. What is the value of X? Okay, so this is the question. This is numerical question, quite easy question, because whatever we have learned in class that iodometric titration, so how we can calculate from there. This is the question from the titration. Okay, so how we can proceed with this? Can anyone suggest? Basically we have to write the equivalent equation. Then I think it is basically some redox reaction is to happen. So from there how much equivalent of chromate is required for how much X equivalent of thiosulfate neutralization. Okay, so if we will see that chromium, when what is happening, so chromate is the oxidative agent. So this dichromate, so dichromate, what is the symbol of dichromate? Cr2O7 2 minus. Okay, so this is the dichromate. Okay, so when it is to oxidize to other people, it is to reduce itself chromium 3 plus. It is mentioned it is in acidic medium, so it is in H plus medium. Okay, by the way, what is the oxidation state of chromium here? Can anyone tell what is the oxidation state of chromium in this chromate? What is the oxidation state? Okay, I can calculate. So there is two what is called chromium, so I can write, we don't know this is what is the oxidation state, I can take as X. Okay, so 2X minus, this is 7, so minus 18, sorry, minus 14, that is minus 2. So 2x is equal to plus 12, so x is equal to plus 6. Okay, Yeah, I think Varun also written. This is +6. Yeah, +6 oxidation state. So +6 is going to +3. So valency is 3. So for two chromates, so it is +6 means this is 6. So valency I can write here. Valency factor xii or zi I can write zi is equal to 6. Okay. And what are the other is thiosulfate. So what is to happen? Thiosulfate. So thiosulfate will be oxidized. So S2O3 2 minus. What is it is to oxidize? S4O6 2 minus. So here sulfur, what is the oxidation state here? 2x minus 6 is equal to minus 2. So 2x is equal to plus 4. So x is equal to plus 2. Right? So plus 2. Here what is the what is the oxidation state here? This is 4x minus 12 is equal to minus 2. So 4x is equal to plus 10. So x is equal to, I can write here as it is 2x. No need to write it this way, 2x. So I can write 2x is equal to 5. Okay, so what is the valency here? J2 valency, that is 1. Plus 4 to 5, it is 1. And here how much? Plus 6 to 3, so this is 6. Okay, so now okay, how we can write? So the equilibrium. So now what we can write? So whatever equilibrium amount of chromate is required, how much how much equivalent of thiosulfate. So I can write these things, that Z1 M1 V1, that is Z2 M2 V2. I think all people know this thing in the during what is called BSc time, when we used to do the titration and we used to calculate how much equivalent amount of titrant is required, how much equivalent of titration for the titration. Okay, so this is the equation. Also some people used to write V2 S2 is equal to V1 S1 like this. So there is different type of things is there. So this is the equation. So basically for redox process we used to use these things. So suppose this is for chromate. So chromate Z is equal to 6 and M1. So M1 it is given 0.1 molar dichromate. So into 0.1 into V, that is 25 ml. Okay, and for thiosulfate, what is there? We have to calculate the X value. So that Z value, it is given 1. What is the value X? And 25 ml of thiosulfate. Okay, so I think so 25 it is cut down. So this X is equal to 6 into 0.1, 0.6 more. Okay, so this way you can calculate. So answer is the C. Okay, this question also came in June 2016. So on the titration conductometrically, a NaOH solution with a mixture of NaCl, hydrochloric acid and acetic acid solution. Plot of a volume of mixed acid added B in Y against the concentration A in the x-axis is expected to looks like. So basically this is acid-base titration, conductometrically the acid-base titration. So it is given that you have you are adding NaOH solution with what is called conductometrically a NaOH solution with a mixture of HCl. Okay, so basically in the y-axis concentration of A on the expected. Okay, so basically you have taken A, that is NaOH. So basically in the container you have taken NaOH, and you are drop wise you are adding HCl and acetic acid mixture. Okay, now a plot of a volume mixed acid on the B. So on the y axis, what is volume of the acetic acid or HCl and acetic acid, and x axis it is the concentration A, x axis of A, that is NaOH. Okay, so now how the graph looks like. Okay, that is the basically on the x-axis, or this is the conductance value, and these things you have the concentration of HCl and concentration or volume I can write HCl and acetic acid. So this is the thing. So now question, how it will be looks like. So I think we already have discussed with concentration how the what is called conductivity will change for weak electrolyte, for strong electrolyte. All these things we have discussed. No, for one graph we used to retain that this is the square root of concentration and this is the conductance. How it used to. For strong electrolyte, if the dilution will increase, then your conductivity will increase, and for weak electrolyte it is to like this. We also discussed that why these things is happening. This is for strong electrolyte and this is for weak. Okay, so for strong electrolyte, why with dilution the conductivity is increasing? Can anyone tell? Then we can come to this problem, then it will be more clear. Anyone can unmute. I think these things we already have discussed. Okay, so means strong electrolyte, what is happening? Means suppose you have taken NaOH, which is a strong key electrolyte. So when you will dissolve in the electrolyte, what it will happen? So it will completely dissociate. When it will completely dissociate, it will form Na plus and OH minus. Okay, and when you will dilute the solution of that solution, then what will happen? Na plus and OH minus, it will be go far away from each other, so there will be no Na plus and OH minus interaction, so it can move fast in the solution. For this, the conductivity is increasing with dilution. But in the case of weak electrolyte, what is happening? In the weak electrolyte, your electrolyte is not completely dissociate. Okay, so for that, what will happen? When you will dilute the solution, it will dissociate, so the number of ion will be increased, so the conductivity will sharply increase. Okay, so now we can come to the in the question, because what is called for strong electrolyte and weak electrolyte is there. So in the question also you can see you have the strong base and we have two acid. One is strong acid, another one is weak acid. Okay, so that means in the container NaOH there, so you have the OH minus. So if mixture of HCl and acetic acid if you add, then what will happen? So OH minus and Na plus is there, and you are adding H plus and Cl minus plus acetic acid. So this H plus will react with the OH minus and it will form water plus NaCl. So on what is called table, we already discussed that what is called as first highest conductivity in different ion. So there we see that H plus ion conductivity is most, after that OH minus. So here you can see H plus and OH minus is forming H2O. So that means your concentration or your conductivity will decrease. Okay, so here you can see here in the option A, here also it is decreasing, here it is also decreasing, but in the here it is not decreasing. Here also the conductivity value it is decreasing. That means C will not be. So option C cut down. So we have three options: A, B, and C. A, B, and D. Okay. Now when you are adding HCl and acetic acid, then what will happen? So when all the NOOH will consume, then extra, so it will decrease some point. Suppose this point it is reached, here also this point is reached. Okay. Oh, okay. So the here what we are seeing that this is the conductivity, no? So this is increasing. So this will not be the case. So C, that might be option C. This is because decreasing, so it will decrease. So A, C, and D will be the option. After that means B is cut down. Now when NaOH is completely neutralized, then what extra HCl and acetic acid you are adding. So when this will extra you will add, then H plus and Cl minus will form and acetic acid, whatever it will be. So it will be, that means your in the solution H plus ion concentration will increase. So your conductivity value will increase. So here you can see the conductivity value is increasing. So D will be the answer. So now question, why A and B or A and C is not happening? Because we are mixing from the top HCl and acetic acid. So whatever solution is there, so continuously you are adding. Okay, so whatever in the solution, all these four pieces will be there. Sorry, not four, three pieces will be there: H plus, Cl minus, and acetic acid. So there will not be something that initially your HCl is what is called participating for the conductivity, after that acetic acid is participating. So that is not the case. So for this C and A will not be the answer, D will be the answer. Okay, is it clear? So I can just recap all these things. So basically you have NaOH solution on the container and you are adding HCl and acetic acid, and what is called HCl acetic acid, that will neutralize to it will form NaCl and water. So water and NaCl. So that means in your solution H plus, OH minus and H plus, that concentration is decreasing. For this your conductivity value will be decreased. When it will go to the equivalent point, your conductivity value is decreased. So after that when you add excess amount of HCl and acetic acid, so H plus ion concentration will increase, so the conductivity value will be increased. So for this again it is increasing. So and okay, option D is the answer. So we can go to the next things. So the standard electrode potential E naught at a fixed temperature and in a given medium is depend on only the electrode composition and the extent of a reaction, the extent of electrode reaction only, the electrode reaction and the electrode composition. What will be the answer? The standard electrode potential E naught. What we is to discuss, E cell is equal to E naught plus RT by NF ln ox by rate. Okay, so this E naught, that is the standard electrode potential. Okay, so this E naught, it's depend on what? The activity of the composition. Suppose you have taken AgCl, this is the reference electrode. Then what is called, its potential is 0.196 volt. So this depend on the concentration, whatever composition Ag and AgCl, it is dipped in the KCl solution 1 molar. So depend on what are the composition you have taken. So that means what are the reaction is happening, and means what are the composition you have taken, that is one option. Other things are the what are the reaction is happening, because in AgCl, that reference electrode, the potential or reference potential, that's depend on the activity of Cl minus. So because you have taken the KCl, so this AgCl, this Cl and the KCl that will be in the equilibrium. So the activity of the Cl minus, that is responsible for the potential of AgCl. So that means what reaction is happening on the electrode, as well as what are the composition of that electrode. So option D will be the answer. Okay, so the next question, the aqueous solutions of NaCl, calcium chloride and lanthanum chloride show the following plots of logarithmic of mean ionic activity coefficient versus molar concentration. Okay, so which one is for which component? So there is three chemicals is there. One is NaCl, one is calcium chloride, one is lanthanum chloride, trichloride basically. So what will be the answer? I think this what is ionic activity coefficient, so that things we already discussed in the class. So what it will be the answer? I can write for some hints. I can write the ionic what is called ionic activity coefficient, that is log of sigma plus minus, that will be minus 2.303 a mod of z plus z minus root of I. What is this? I is ionic strength. Okay, so this is the things. Now I think people can tell the answer. Which one will be the things? So one is ionic conductivity, that is high A and B and C. Which one will be the answer? Can anyone tell? I can give another hints. This is hints number 1. Hints number 2 is same concentration. So this question, what we can check that log of gamma plus minus, that is minus 2.303 a z plus z minus, this z plus z minus, that is the charge of the ion, like suppose NaCl. So what it will produce? Na plus and Cl minus. So Z, this is the Z plus and this is Z minus. So for Z plus, this is plus 1, Z minus minus 1. Okay, so that means if you see the mod value of this, like mod of Z plus Z minus root over I. So this value for which one it will be bigger and for which one it will be smaller. I think these things you should tell. Calcium chloride, what it will be? Calcium 2 plus plus 2Cl minus. Lanthanum 3 plus plus 3Cl minus. Okay. Now if you see this question, so for this value, because Z value for sodium plus, this is plus 1, this is minus 1. So plus minus, that will be 1. So 1 to the power I. So for sodium it will be, so sodium it will be root to the I, and for calcium how what it will be 2 plus and this is minus, so it will be 2 root I, and for lanthanum this is 3 plus and Cl minus 3 root I. Okay, that means this value for sodium chloride it is less, and for calcium chloride it is medium, and for lanthanum trichloride it is highest. But the interesting thing is that there is negative value is there, one negative sign is there, no? So that means if negative sign is there, then whatever value, this value will be low, the slope that is negative slope, that will be low. So here in this A, B, C, where in this case which one will be low slope? This is A, this is B, this is C. So you can see C is more steep, that means it is more negative slope. B is medium and A is less trip. For this it is coming like this. So A is the less negative. That means this will be the sodium chloride. And B is the medium. Which one is medium? B is the calcium chloride. And lanthanum, that is more, this value is more positive value, means high value, but it initially it is minus, so the what is called slope will be more, so that more negative, so that is lanthanum trichloride. So which option it will be? A is sodium chloride, means B and C possible, but B is calcium chloride, so B is the answer. Okay. So Colora's law we have also learned in the class. So from the Colora's law, okay, there is some question. So actually in the Colora's law, whatever we have discussed, suppose NaCl is there in the standard condition, what is to happen? Na plus plus Cl minus. So Colora's law telling that at the standard condition, the activity or the conductivity of the NaCl, that is equivalent to the component of Na plus, means conductivity of Na plus plus conductivity of Cl minus in dilute condition, at dilute condition. Okay, so this is the Colora's law is to tell. So in Colora's law there is the another condition also there. So this is the in the standard condition, but in normal whatever experimental condition, that is to discuss or express in this equation. Okay, so the question is in Colora's law, lambda m is equal to lambda m naught minus k root to the c. So c is the concentration. Okay, so asking that this lambda m naught and k, so these two factor, depend on which things. One is depend on the stoichiometry, depend only on specific identity of the electrolyte, or depend on specific identity of the electrolyte, depend on or independent on specific identity of the electrolyte, are mainly depend on specific identity of the electrolyte and the stoichiometry respectively. So what will be the answer? This is quite easy. If you understand this thing, then you can answer this question. This lambda naught. So this thing depend on what? Identity of the electrolyte means basically, suppose you have suppose calcium chloride. Then what it will happen? Calcium 2 plus plus 2Cl minus. So in this case, lambda m of calcium chloride, what it will be? Lambda naught of calcium 2 plus plus 2 lambda of Cl minus. So that means what are the electrolyte or what are the electrolyte you have taken depend on that this lambda value will be vary. So that means it is specific identity of the electrolyte. Okay, and this stoichiometry, how many ion is there? So this is the stoichiometry. So it's depend on the identity of the electrolyte as well as stoichiometry. Okay, so the answer is D. So the next question is the concentration of a magnesium sulfate solution having the same ionic strength as that of a 0.1 molar sodium sulfate solution. Then we have to calculate what is the concentration of magnesium sulfate. This is the question. This is quite easy. If people can do this thing. So ionic strength, basically you have to write that one, ionic strength equation. First we have to calculate the what is called ionic strength of sodium sulfate for 0.1 molar solution. Then from there you will get the ionic strength of sodium sulfate. Then you know from, because it is told that ionic strength of magnesium sulfate and sodium sulfate is same. Then from there you have to calculate the concentration of magnesium sulfate. So this is the hint. How we can proceed? Ionic strength, what is the equation? Can anyone tell? Ionic strength, I, that is half of sum over mi zeta square. This was there, no? I think we have already discussed this thing in the class. I mean, professor have discussed. So I can do in this way. So you people also can do with me. So first we can calculate for ionic strength of sodium sulfate. So what it will be when it will dissociate? 2Na plus SO4, 2 minus it will form, right? So it is 0.1 molar. Then this one, how much it will be? 2 into 0.1, because it will completely dissociate. This one it will be 0.1. So we know the concentration. Now we can put in the equation. I is equal to half of m1 z1 square plus m2 z2 square. Okay, half of, suppose this is for cation, this is for anion. Okay, so cation M1 is 2 into 0 0.1, so 0.2 into 1 square plus M2 0.1 into minus 2 square, so half of 0.2 plus 0.4, that is 0.3. Sorry. So I extend for what is called sodium sulfate we got. So for magnesium sulfate, what you can write? Magnesium sulfate also you can write this way: magnesium 2 plus sulfate 2 minus. Suppose the concentration of magnesium sulfate is m molar. Okay, then if it is m molar, then how much m molar of magnesium will form and m molar of sulfate also will form? Then I can write ionic strength I is equal to half of M1Z1 square plus M2Z2 square, same. Then half of, this is M1, M. So this is Z1 square is plus 2 square plus M2, that is M, and sulfate also minus 2 whole square. So this ionic strength it is given 0.3. So this value it is given 0.3. So what we can write? 0.3 is equal to half of 4m plus 4m. So how much it will be? 0.6 is equal to 8m. So am is equal to 0.6 divided by 8. Is this? How much it will be? Can anyone tell how much it will be? 0.0 then 60 8756 485, that much. Okay, so this way you can do. So answer is C. We can go to the next problem. Okay, so 10 ml aliquots of mixture of HCl and HNO3 are titrated conductimetrically using a 0.1 molar NaOH and a 0.1 molar of silver nitrate separately. The titrant volumes are V1 and V2 ml respectively. The concentration of HNO3 in the mixture is obtained from the combination of these four options. Okay, so basically what is, I can simplify the question. Basically what it is asking, so means you have one mixture of HCl and HNO3 to means in the 10 ml of solution which contain HCl and HNO3, and that solution you are titrating with 0.1 molar NaOH1 and another time 0.1 molar silver nitrate, separate. Then asking that if the titrant volume are V1 and V2 ml respectively, means when NaOH you are using, that time the titrant volume NaOH volume is V1, and when you are using that time volume is V2. Okay, now telling that what is the of nitric acid in the solution. HCl and HNO3, that is the mixture. So there how much the concentration of nitric acid? So this is the question. How we can calculate that thing? How we can proceed? First we can check one by one. Okay, So the first titration we are doing with HNO3. So first titration what we are doing? First titration I can write titration. First titration what you are doing? So I have HCl plus HNO3 with NaOH. Okay, so this is the thing. So this HCl HNO3, that is 10 ml. So what will form? So when it will form NaCl NaNO3 plus H2O. This is the thing. Now we don't know that how much HCl is there and how much HNO3 is there. Okay, so let's say HNO3 HCl is N1 molar, and HCl and HNO3 is N2 molar. Okay, and it is in the 10 ml of solution. That means what is called, we know that N1 plus N2, whatever molar equivalent of nitric acid and HCl, that will be equivalent to the what is called concentration of NaOH. So that is 0.1 molar into V2. Sorry, that is V1. I think I can write. So that is V1. V1. So this is one equation. Because when you are titrating, so at the equivalent point this thing will happen. So whatever, suppose N1 and N2 molar of HNO3 and HCl, so that is it is equivalent to 0.1 molar into V1 volume of the NaOH. Okay, and the second case, what is happening? Second titration. What is happening? So second titration, what is happening? You have the HCl and you are adding silver nitrate. What will happen? Silver chloride will be precipitate and HNO3 will form. Okay, that means the HNO3 whatever moles, that is increasing. So what we can tell is that number of mole of HCl, that will be equivalent to number of moles of HNO3, sorry, silver nitrate, AgNO3, because you can see one equivalent of HCl that is reacting with one equivalent of AgNO3. So then we can write N1, that is 0.1 into V2, because silver nitrate it is V2 ml of solution is required, right? Now number of moles of HNO3, because here HNO3 is producing, so number of moles of HNO, only HNO3 I can write, that will be N2. So N2, what we can write? N2 I can write N2 plus N1 minus N1. This way also you can write, because N1 plus N2, here you can see N1, I just add here, but again subtract that. So N1 plus N2, that I have written here, where it is, this one, N1 plus N2, that is 0.1 V1 plus N1, that is, where is N1? Here N1 0.1 V2, so that means 0.1 common V1 plus V2. So this 0.1 and you are what is called titrating with 0.1 molar NaOH, so that means that will be cut out. So you have the V1 plus V2. Okay, so the answer, oh sorry, not V1 plus V2, this is minus So this will be minus, this will be minus. So V1 minus V2. So A is the answer. Okay. So next question is, given that E naught for Cl2 Cl minus is 1.35 volt and Ksp value is given. So solubility product, it is given at 25 degrees Celsius. So E naught corresponding to the electrode reaction. So this is the electrode reaction. So what is the potential of that electrode reaction? So this is the question. I think these things we already, this kind of problem also we have done earlier also, and this is just from the solubility product problem. So how we can proceed with this? All the things whatever it is given, so we can proceed with that only. So I think reaction 1 what is given. So this thing it is given, what is the reaction? Half of Cl2 suppose plus 1 electron, that is going Cl minus. So E naught it is given 1.35 volt. Okay, and Ksp value it is given. So Ksp value what we know for AgAgCl it is so AgAgCl what it will be? AgAgCl Ag plus Cl minus is there. So we know that E cell E naught E cell is equal to 0.059 divided by n log of Ksp. This equation we know. Now for this case n is equal to what? 1, and Ksp value it is given. So E naught we can calculate. So E naught is equal to 0.059 by 1 log of 10 into 10 to the power 10 to the power minus 10. So this is the thing. So 10 into 10 to the power 10, it will become 0.59 log of 10. So this will be 0.59 volt. So it is approximately, you can write 0.6 volt. Okay. This is the things. So this is the equation 1. This is equation 2. So it is given on equation this thing. So what we can write? So these things, half of Cl2 gas plus Ag plus in solution plus 1 electron, that is giving AgCl. So we can write what is that? Suppose this is E1, this is E1, this is E2. What we can write? Here n is equal to n3. Suppose this is E3, this is n3. So what we can write? E3 is equal to n1 E1 plus n2 E2 divided by n3. Now you can, whatever value you can put 1.35. This is the E1 value plus 1 into 0.59 or 0.6 I can write divided by 1. So 1.35 plus 0.6, that will be 1.95 volt. So D is the answer. Okay, so this is a quite easy problem. So means what are the things it is given in the problems, and after that we can follow the things. Okay. Okay, I think these things is there. I think this is we can discuss in the next class, because for this we need some thermodynamics. I think next class we will discuss on this topic. Okay, so thank you all. If anyone has any question, you can ask. Anyone has any question? Cyclic voltammetry part, that things is clear, I hope, because I have taught the cyclic voltammetry, because next class waste handling thing will be discussed. After that battery metrology will discuss. So in the battery metrology, there we need the cyclic voltammetry, all these things. So that time when I will talk that something related to battery, so that time I think it will be helpful. Okay, so if anyone has any question, you can tell, unmute and you can tell. Okay, I think all the things is clear. So if you people have any doubt, then you can send the mail. I think once I have send the mail to the this group, so you can write to me the mail. My mail ID is Suhonkor. Okay, I think have to go. So Suhonkor m1@isc.ac.in. Okay, so this is my mail ID. So you people can keep any inquiries there. You can write to me. Okay, and I think we can conclude the session. So we'll meet to next week. Have a good day. I think we can close the session.